Thank you for coming to my talk. Today I'm not just going to talk about the work I've been doing during my PhD at ANU. I'm going to try and broaden the scope a bit and talk about the work we've been doing at Geoscience Australia to both improve the datum and how that's feeding back and improving the positioning service with GPS. I think these days most people understand how GPS operates. We need to have 4 satellites to get a position. They're orbiting us at around about 20,000 kilometres up, and we now have a full constellation of around about 31 satellites that we can access. They transmit on L1 and L2 for all of the satellites. This is around about 1500 and 1200 megahertz. The new satellites are now transmitting on L5, so we're having a greater range of frequencies, and that sort of opens the door in what we can do. There's a distinct difference between how a handheld receiver works, or how your sports watch works, and how geodetic equipment works. The biggest difference is in the antenna that observes the observations. You need to have a very well-performing, well-behaved antenna to get good range measurements. The other thing is the type of geodetic receiver you need to get those observations from. But as time is going on, we're beginning to see that line is beginning to blur a bit, and I'll talk about that a little bit later. From a general user's perspective, for people just normally using their handheld receiver, the biggest jump in precision was a bureaucratic one from Bill Clinton. In 2000, he decided to take off selective availability. And we went from a positioning system where we couldn't distinguish where we were on a city block or decide if we're on top of a skyscraper or below a skyscraper, to a positioning system that anyone could use and work out what side of the road they were on and basically how many floors up there were. So that was a big change, and I think that perked a lot of interest, and then we've seen a plethora of applications begin to grow on this positioning system. We used to talk about the possibility of being able to do automated farming and automated roadworks, and these days it's becoming to be more of a routine, and we're driving the position down, the position required. We're beginning to see the emergence of UAVs, and eventually automated driving cars is on the way. What is interesting is now people are proving the concept that you can position just using your smartphone with that antenna to the centimetre level, just with what you have in your hand. There's more work to go in terms of how we actually achieve that, but the proof of concept has already happened. Along with this precision gain, there's also been a big improvement in the number of satellites that are available. It's not just from GPS, and GLONASS has been operating for a while, but from the other systems supported by the Europeans, such as Galileo, and more the Asia-Pacific region in specific, Beto, QZS, and India. And what that means for Australia is we're right in the middle of everything that's happening and developing in global navigation. We're stuck in the middle of the hotspot, where we can see these new constellations from the Asia-Pacific regions, where other parts of the world can't, and we still get the benefit from the American and the Russian systems as well. As these applications are becoming to need more precision and more accuracy, what people are beginning to realise is if you really want to operate in that sense, you have to operate in ITRF. ITRF is seen, the International Terrestrial Reference Frame, is seen as the standard for coordinates. If you want to get the most precise coordinate and maintain that precision throughout, you need to be operating in ITRF, whatever you're doing. How the reference frame is actually realised and how we maintain that precision is you use a variety of different observing techniques. They use VLBI, satellite laser ranging, and DORIS. But the most dominant source of information for this reference frame is GPS. ITRF has around about 800, nearly 900 stations. Of that, nearly 700 are GPS used to determine that reference frame. So the way that GPS goes into that reference frame is through an organisation called the International GNSS Service, IGS. And it's quite a unique kind of organisation in that there's over 200 different organisations all around the world contributing to this high precision service. And they aim to sort of support earth science research and provide access to high precision applications. So Geoscience Australia provides a lot of data into the IGS organisations. We're actually up there in the top 3, top 4 sort of agencies, making that data accessible for everyone to use. And It's good to see. What else Geoscience Australia has become recently involved with is in actually producing the analytical products that go out there for public consumption for higher accuracy applications. And there's three main products. There's the ultra rapid, the rapid, and the final. The slides are very bad, I'll move on. The three main products are the ultra rapid, rapid, and final. The final product comes out with a latency of around about 2 days, and if you're a scientist trying to work out the most precise solution you can, if you're trying to work out crustal motion or see what's happening to the crust for sea level monitoring, you want to use the final products. But what we're seeing is that there's a much bigger demand for the ultra-rapid products. If you're doing real-time positioning, you're going to use the most precise orbits that can come out and have the predicted values. And so the biggest demand is for the ultra-rapid. What you're seeing in these products with time is that there's a decrease in precision with time. If you look at the broadcast ephemeris that you get from the GPS, we've gone from knowing the orbits of the satellite around about 5 metres in accuracy. If you look at the most precise products and you look at the different analysis centres that are contributing to those products, you see we're coming down to around about 10 millimetres in terms of knowing where that satellite is at any particular point in time, which is quite remarkable. And what is even more remarkable is that these 6 to half a dozen so agencies, all computing their own solution, are now agreeing with each other to within a 5 millimetre level for a satellite 20,000 kilometres up. What is good to see is that this is also being supported in the predicted orbits, the things that are needed for real-time applications and everyday use. We're now getting down to a predicted accuracy of around about 25 millimetres for the satellite orbits. If we go back to the reference frame, every time a new reference frame is realised, it's not just ITRF, you have ITRF at different epochs. And that comes about when these different analytical agencies reprocess the big time series from about 1996 through to 2014. And they consistently apply the latest modelling into their software. And in the last one that was just completed, they expected a precision improvement from physical modelling such as how they model the troposphere, allowing for horizontal gradients, how they model ionospheric corrections, and how they model various orbit manoeuvres and solar radiation effects. To improve the accuracy of the reference frame, they're relying on the antenna model. Now, this antenna model is derived from robotic calibrations, which we are now doing at Geoscience Australia. And I'll talk about that a little bit more. So to improve the reference frame, one of the key areas is in the antenna modelling. The results from that GPS processing campaign is you begin to see that we're going down to around about less than 2 millimetres in terms of precision of our station coordinates with time. And we're getting down to 4 millimetres in height. This is getting to be quite a remarkable achievement. This is for over 700 stations in the 600, 700 stations in the solution. While that looks really good in terms of precision, if you do a spectral analysis of it, what you see is very big peaks in the annual, semi-annual and the corresponding harmonics with time. And that's indicating that either we're seeing some very big geophysical effects around the globe, or there's some still systematic effects present in the GPS processing that need to be resolved. And it's a bit of both. I think it's the conclusion. So the result of that reprocessing, computing the two new reference frame, there wasn't a huge jump in realisation between the two reference frames. So we can see that they seem to be getting a bit more consistent in time. What was new in that reference frame was how we deal with stations that have been affected by these massive earthquakes that have happened in the last 10 years, the post-seismic deformation events. And while there's been a lot of attention at sites located very near the event, what we're finding is that maybe even though maybe it's something that we actually need to take account in Australia. When we to start off with, the seismologists were telling us that we should expect some kind of deformation in Australia, just looking back at the earthquake record. But when the geodesists were looking at the results, they were saying we can't see it. We've only got a network of around about 12 stations and we can't get a velocity below 2 millimetres level and there's no way we can detect the amount of deformation that you're talking about. So in the last 5 to 10 years, we've been fortunate enough to received a lot of funding to have the Ozscope network built. So we've gone from a core network of around about 12 stations to something that's approaching closer to 100 stations around Australia. And what's most important is that these stations have been designed specifically in mind to monitor crustal motion. So they're high quality stations. They're not just something that's just been thrown up. What that's allowed us to do is move from a very sparse sort of velocity field map that you get for the plate tectonic motion to something that you can begin to see with a greater deal of resolution. And we've just produced the latest plate model for Australia, and when you look at the residuals of that velocity from the plate model, you can see that we've increased in an order of magnitude in the last 10 years. We've gone from something that fits at the 3 millimetre level, 2 millimetre level, to something that's down to the 0.3, 0.2 millimetre level. So we can now start detecting these interesting signals within the Australian crustal plate. And this is only from a network that's been observing for less than 5 years. If you want to get a good precision from GPS, you need a long time series. And to be able to get this result so soon is astounding, and it'll be interesting to see what happens in the future and what other signals we can detect. So what we are seeing is that these large earthquakes are actually causing deformation in Australia at the 0.2 millimetres per year, 0.2 millimetres of a year, and we can detect that in our GPS observations. For instance, you look at the Macquarie earthquake, and if you look at the station in Hobart, HOB2, you can see that's a significant change in velocity straight after that earthquake. Again, from mobs, coming a little bit further north, there's still an impact from that one event. And just across the road in Tidbinbilla, we can still see that effect. So while we've seen that these big earthquakes can affect us now in our observation span, it's sort of interesting to try and work out how these big earthquakes have affected us in the past. What sort of impact will they have on these time series that we haven't modelled? So if we're going to go on and try to detect these very small signals within the plate, we need to try and reduce these systematic errors that are still present in the GPS time series and improve their overall accuracy. And as I mentioned earlier, a big part of that is understanding how the antennas behave on our observing stations. And as part of that Ozscope funding, again, we've begun to set up an antenna calibration facility at Geoscience Australia. So what is actually antenna calibration? What am I interested in this? It's trying to answer that fundamental question. GPS relies on being able to compute a range from the satellites to your receiver. And you've got to ask yourself, exactly what is that range measurement? Where exactly are you, where does it start and where does it finish? Where does it start from the satellite and where does it actually finish in the antenna? And what you find is that there's no one distinct point where that range measurement is actually occurring. It changes with time and it changes with where that satellite is actually with respect to the antenna. So I'll just try and go over that again. If you had an ideal antenna that didn't have any effects and performed beautifully, as the satellite moved over the station, you'd have no change in phase. You'd just have a complete constant, and our modelling and accuracy would be significantly better already. What really happens is that as the satellite passes over the antenna, the phase variation changes and that location of where that range measurement occurs is actually biased as it goes over. The first order effect is how it is with elevation in the antenna. The second order effect is where it is with respect in azimuth, so you get azimuthal variations as well. So what the robot is doing back in the compound, I'm sorry the movie's not playing, what happens is you assume a mean phase center offset, and what that antenna will rotate around that phase off center and work out the phase center variations in both azimuth and elevation. So that's why you see it contorting in a funny way. It's trying to work out those errors. The results we've been getting from that robot have been quite good. When we look at one antenna and calibrate it multiple times, we get repeatabilities down to 0.001 0.1 of a millimetre across azimuth and elevation. And I start looking at that graph and I start stressing out about one observation that's 0.15, 0.2 of a millimetre different and wondering if I should include that or not. So the repeatability is very good. What's recently happened is we've now recognised as an IGS antenna calibration facility. We've calibrated well over 100 antennas, and those calibrations are now going to go back into IGS and they're going to become part of the official antenna, IGS antenna files used for reprocessing for all the other analytical agencies. So this is beginning to help to try and improve the absolute accuracy of GPS as we go through. While calibrations can be very repeatable and they help improve the overall accuracy of the system, we have to keep in mind that antennas behave very strangely. As soon as you take an antenna from the calibration environment and move it onto what you're actually observing on, those characteristics can change. And those characteristics are due to something called the near field effect. It's the electrical properties of the antenna change if it's not identical to what's on the robot. To demonstrate this, a researcher in Germany using the anechoic chamber wrapped an antenna cable one direction around the antenna and then wrapped it just once in another direction. And that induced an error of around about 2 millimetres at the low elevation angles. Remember, we're expecting repeatabilities of around about 0.1, 0.2 of a millimetre from the calibration, and to have that effect from an antenna cable. I should point out that some antennas are more susceptible to near-field effects than others. So if you use a survey-grade antenna, it might be more susceptible to near-field effects than a geodetic antenna. So there's that also to take into account. To try and work out how this might affect observations that we're doing today in the GPS network, we took a standard antenna that's out in the field quite a lot, an AOD antenna, and calibrated on the robot. That's the red line here. And what we can see is that compares very well with the actual mean of, for that antenna's values. What we did next was we put a cardboard cutout that sort of, well, not a cardboard cutout, like a piece of plywood that was approximate to the same reflectance properties of concrete. So it was like simulating putting an antenna directly onto a concrete pillar. And we did the calibration again. And that gave us the green line, if you can see it. We're now dropping down to around about 3 millimetres different from what we were calibrating before. You then put on a radome over the top of it, which is very hard to calibrate on the robot, and that introduces another little bit of a bias into the solution as well. So while you might have very precise calibrations, in order to make use of that, is you have to make sure that it reflects the environment you're installing the antenna into. So my take-home message is that we either have to start calibrating these antennas in an environment which is very similar to how they're being installed, or we need to start moving these antennas away from these reflectors in our observing network. This is where my PhD study came in. And I was interested in how to account for these errors, because I thought it was going to be very hard to calibrate a full near-field environment in the field on a robot. And I was looking at a way that I could, through the analysis of long time series, how we might be able to account for this. I was particularly interested in antenna effects, uncalibrated radomes, and how multipath can affect the solution. So that's the reflection of the signal. So this slide is just trying to cover what the effect of multipath is. So you have a direct signal that comes into the antenna, and you have a signal which is reflected off of the ground. And that path difference can cause a bias in your range measurement. The main driver of what that bias is going to be is how high that antenna is above the reflecting surface. So if you have an antenna which is very close to the ground, you have a very slowly varying bias with elevation angle. Down here you have from 10 degrees to 90 degrees, and you see that varies very slowly. If you mount that antenna higher, you have a bias which varies quite frequently with elevation angle. If you change the frequency to L2, that bias gets larger, and if you look at how we actually process the data in geodetic observations, we use a linear combination of L1 and L2. It's a mathematical sort of trick to get rid of the ionosphere, and what that does is it actually amplifies these errors. as well, so they get larger. Fortunately, in the large case, it seems to average out and move more towards white noise, but when the antenna is close to the ground again, you can see that there's more of a systematic bias in your solution. So to try and illustrate that, I did a number of simulations. The top one is for a low monument, and the bottom one is for the high monument. And what you can see is it does look kind of what you'd see in a GPS time series, which I'll show later on. It does kind of look realistic. For the low monument, you have something that looks like it has a lot of time-correlated noise in it, and there is a large bias. It's around about 26 millimetres in height, the bias. For the high monument, you have something which is very close to zero. It's more random noise, but there is still some time correlation in there. If you do a spectral analysis, that sort of comes out. The slope of the spectra is quite a lot higher, indicating high time correlated properties, and is a lot lower for the high monument. What's interesting is when you look at these GPS time series, there's always the assumption that the frequency or that the time series is stationary, so that the errors are consistent without time. But this is far from the case. If you do a wavelet analysis of the time series, what you can see is that the power of that frequency changes with time. So you might get a large variation in annual for a couple of years, and then that will wane for another couple of years. For the high monument, this sort of seems to be smeared out, and that's probably more of the random component in that noise. I think this might have implications for things which are using campaign sort of observations and a low monument. You might have a high peak of noise one year and you come back and that might not be there present in a couple of years' time. Here's an actual GPS time series from the reprocessing effort. And this is from the MIT solution. It's for the Antarctic station Mawson. And what you can see is an interesting signal here. You have something that's fairly consistent up to around about 2008, and all of a sudden there's a large change in amplitude and period in the signal. So my first reaction was that, maybe it could be a site-specific error, or maybe there's something geophysical going on here, or maybe there's another physical modelling error going on in this place. So that's the question we're trying to answer. It's very hard just to do it from GPS itself. So what is nice is if you can correlate it with other observation techniques to try and work out if this is GPS error or really geophysical. So the first step was to try and correlate it with GRACE estimates of elastic deformation at that station. That's the green line up there, and there's a 30-day average there in the red dots of the GPS time series. There is a kind of a correlation in phase between the two, so there is something geophysical, but that generally breaks down after 2008. The amplitude is a lot less than the GPS time series. So it looks like it's something systematic in the GPS observations that are affecting it. And it's not only at Mawson, it's happening at a lot of the other Antarctic stations. It's happening at Casey, it's happening at Davis, and it's like that. If you put those time series on top of each other, you see a similar behaviour. Nice random nature up to 2008, and then a big amplitude increase after 2008. Okay. So the way that I was looking at trying to resolve these kind of errors was to try and look at the processing results and take the residuals from the least squares estimates. So every time you process it, you get a residual of that range to the satellite at every epoch. I stacked those residuals in time and in elevation, and that produced what is like a multi-path map. I call it an empirical site model. So what we have here is the residuals for the station at Melbourne Observatory and MOBS, and I haven't got it here in this talk, but if you did a time series of those residuals over a 10-year period, you'll see that they're fairly consistent over time. They sort of plot over each other, and that's the systematic effect at that station MOBS. If you then plot it in azimuth and elevation over here in a polar plot, you can see that you get these ring effects here which are related to the elevation dependence of the multipath, and then there are some small variations in azimuth. What I found is you could take these multipath maps and apply them all around the world, and it would correlate very well to the local environment that you see. Here's the station in Wetzel. It's one of these super sites like Yarragadee, and it has, well, 5 or 6 antennas in a very small observation span. And at these so-called super stations where there's multiple observing techniques, they have high-grade survey results that go out there and measure the difference between the GPS antennas and the other techniques, satellite laser ranging and VLBI. So what I did was apply this technique to the short baseline and compare it to the survey results. And what you find is that there's not much, you have a bias of around about 1.5 centimetres without doing anything normally, but then if you applied the technique, you actually reduce that bias down to about 4 or 5 millimetres. So it appears that the site-specific effects, the multipath and the antenna effects were one of the contributing factors to this station. Now I've put up this wavelet plot again because it sort of highlights the advantage of doing non-stationary time series analysis. If you look at the spectra of the time series for one baseline, is you see a marked change in the spectral characteristics in the middle of 2012. We've gone from something that's having bands in the time series to something that looks quite a lot more streaky, and there's been a significant change in its characteristics. And if you go back in the log sheets, and you can see that correlates very well with a firmware change implemented on the receiver at a particular epoch. So you can start picking those kind of effects up in the time series. One of the other differences from applying this kind of site-specific models is you begin to see a reduction in the noise in your baseline results as well. So we're also increasing the precision of the observations as well. So that sounded very good and quite promising, so I was quite excited. But it did not work very well in geodetic time series, very long processing time series, and on a global scale. So it worked well on a small kinematic case, but did not work well in a global scale. And what the problem was is I was not accounting for the satellite errors. So I was accounting for errors down here in the ground-based station at the reference station, but I had not thought about the errors occurring at the satellite. So I went back and looked through the time series. Okay. Yep. Went back and looked through the time series and worked out what that error correction should be for each satellite in a 4-year period. And I'm just going to throw up a plot of those results. And the mean correction was of a magnitude of around about, maximum of around about 4 millimetres. So we're an order of magnitude less than what we're seeing at the stations. And a lot of the satellites seem to be, the model seems to be quite good, but there were a handful, half a dozen satellites where the model was not really performing well, and that really needed to have the correction applied. One of the caveats with this technique is that it requires a lot of observations in order to derive a good model. We need to have observations of around about the 3 million level or 4 million level per elevation bin at 0.2 of a degree in order to get a reliable model. If you didn't have that, then you got quite a messy model out there and you couldn't rely on it. So it's best not to apply it in that case. That was only at the 100,000 level, 900,000 level. So you produce a plot, a map of the corrections for the ground station, just using the ground station technique, and then you produce a plot that accounts for the satellite errors. And you look at the two, and I can't see much of a difference between the two. They look absolutely identical. But you take the difference, and you can see these streaks here that occur in the polar plot. And what those are is it's definitely the satellites that are coming out. You can pull out what that correction was for PRN10, and then you can plot up how that PRN10 was flying over that particular site, and they correlate very well. So those systematic effects do come into the sites. To cut a long story short, I did that standard processing that was used for the reprocessing analysis. And I looked at a time span of around about 2010 and 2014. I compared it just using the ground-based correction technique called the ESM, and what you see is that the coordinate repeatability sometimes is a lot better, and other times it degrades with time. So it was inconsistently performing. If you applied the satellite-based corrections for the satellite antennas in addition to the site-specific areas, what you got was a consistent improvement in your coordinates. Now, it's very small. It's around about 0.2 of a millimetre, but it is consistent, and it is a very large statistics base. I think it's for over 700 stations, and that's the nature of GPS processing at the moment. It's very hard to show any level of improvement in GPS. One of the nice things to fall out from it is if you applied this technique, what you saw was that your rate uncertainties, the things that were used to derive the velocities for the plate model, actually decreased. And if you applied this technique, that effectively means you can get clearer results earlier on. I'm well ahead of schedules, but I guess my final remarks to wrap up today is that the results attained from GPS have improved markedly over time, and this hasn't been any coincidence. It takes a lot of effort from a lot of agencies to get this achieved. This is through the ground infrastructure that agency supports, such as GA. It's through physical modelling of the satellites, and it's the temporal latency of the products and the resolution of those products. We are going through a phase where it's getting very hard to improve the GPS precision. It's beginning to plateau, so we're really looking at second order, third order, fourth order level effects to try and improve GPS. What we're hoping is that the GNSS constellations from the other countries is actually going to start helping us to improve these biases that are in GPS in there. There's a other thing around, it could actually start interfering and increasing it, but if we do the proper research and get into there, we might start improving the accuracy. As we go forth and as the positioning sort of matures in Australia, there's going to be even more of a demand for the analysis products that are coming from GA. We're going to need to start having our own sort of analytical products coming out, producing our own orbits and clocks for public consumption here in Australia to ensure that they're of the right value for use. And we're going to need to start monitoring the satellite constellations and ground installations carefully. Thank you. Any questions?